Hello, everybody, and today we will look into the lecture of linear algebra. This is our lecture number 15, and we will be taking the lecture from the MIT Linear Algebra series with Professor Gilbert Strang. Um, I will like to describe what it means when we say that we have a projection matrix. Now, let's assume that we have a system which is known as AX equal to B. And in this system, AX equal to B, B does not belong to the column space of A. But we want to make a best guess. So we will take our column space and we'll try to project this B onto the column space, and we'll try to find the best representation of B in the column space of A, which happens to be our projection vector P, um, that resembles and in some way is very closest. When we say very closest, it means in the mean square sense it is the least distance thing between B and the column space A. So we will drop a perpendicular. As you can see, we have dropped a perpendicular on the column space. Let's assume our column space is just this line, which is described by this vector A. Since it's a one-dimensional, so it basis contains only this vector A. So we drop from B a projection on A, which actually meet at point P. Okay, so this P vector is the projection of B along A, whereas this E is the error vector, and the error vector is the perpendicular vector on A. So E is P minus B. Now, if you wanted to find um, this particular P, what we can see very clearly here is that actually this P vector, which is from origin till this point P, this is the P vector, is actually some scalar multiple of A, because it is along A. So it will be like one half of A or one third of A. However, but it is some scalar multiple of A. So we have to find the scalar multiple of A. So X is a scalar multiple of this vector. So keep in mind, this is a number and this is a vector. And once this number is multiplied, this scalar is multiplied with this vector, we get another vector P. So we are trying to find, in order to find P, we know A, and now X is the unknown. We wanted to find this scalar multiple along A. In order to find it, we can use the fact now is that this A and E are orthogonal to each other. And we know that when two vectors are orthogonal, then the A transpose times E is 0. And now what is E? E is B minus XA. So B minus P, which is B minus XA. So A transpose times B minus XA should be 0. Now, if I open this matrix equation up and expand it, I will find out that this is actually equal to X. X is a number right now, or a scalar, and A transpose A, now this is A transpose A, is equal to A transpose B. So now this is a vector equation, and now A transpose A. Now keep in mind, A is a column vector. So once you do the transpose, it becomes a row vector, and the row vector multiplied with a column vector will give you a number. So this A transpose A is also a number, whereas A transpose B is also a number, because A is a column. When you make it a row and B is column, so row multiplied by column will always give you one number. So this is a number, this is a number. Now X will become equal to A transpose B divided by A transpose A. So this will give us the X. So now X is A transpose B over A transpose A, and this X is the same X that you actually wanted to know. So once you know this X, then you multiply it with A and you will get this P vector. So projection is a lot easier to find in case of one dimensional column space. Now keep in mind, what is one dimensional column space? It means your A matrix, Ax equal to B, this A matrix actually contains only one column, or it contains two columns, but they both are not independent. One of them is independent and the other one can be made from the linear combination of the first column. So it means that the rank of this matrix is 1. So in this situation, it is just one number on the top divided by another number and you get an x. However, the situation can be extended to a much better generalization, which is if your column space is not one dimensional, if your column space is two-dimensional, three-dimensional, or more than three-dimensional. In this case, how you will find the projection? So in order to find the situation where we want to find the projection for this one, we will basically try to look at this particular situation. Now, if you look at it, in case of one-dimensional column space, your P is A into A transpose over A transpose A. So now this particular A transpose B over A transpose A times A is your P, and this is the scalar multiple that you want. Okay, and now we go for this matrix. This whole thing A transpose. Now keep in mind, if I do A transpose, then this will give me a matrix. Whereas if I do A transpose A, this will give me a number. So here, this A transpose over A transpose A is not canceling out just because A transpose is a matrix, whereas A transpose A is a number. So a matrix divided by a number gives you this projection matrix, this capital P. So whenever we wanted to find the projection, we will take this matrix multiplied with this particular vector, and this will give us another vector whose name will be projection vector. So this is a projection matrix, and the projection matrix is defined by A transpose over A transpose A. Now let's move into a situation where we don't have what you call them a line. Rather, we have something which is much more suitable, where let's say we have a system AX equal to B, and where the column space is not just one dimensional, it could be two or three dimensional. But the main thing is it may have no solution. That situation tells us that A is a tall matrix. So in the tall matrix case, AX equal to B may not have a solution. So B does not fall in the column space of A. So in this situation, we can extend our previous theory and we can say that instead of finding AX equal to B, we'll try to find AX hat equal to B. So what is X hat? You see, now we replace B with the P. Now, the moment we replace B with the P, we have to replace X with the X hat, whereas A remains unchanged. So this X hat we can find because now P belongs to the column space of A, whereas B does not belong to A. So this system doesn't have a solution. However, this system does have a solution. Now, how to find P? Where P is a projection of B, P is a projection of B onto the column space of A. So how we find the projection of B onto the column space of A, where A is not a line right now. It could be a plane or it could be something different than a plane, but it is not one dimensional. So in that situation, we cannot use a number divided by number the way we did it last time. Okay. So we will go for the solution now. You see, now we have a complete column space which seems to be a plane here. So it's a more generalized picture. So now we have a plane and we are dropping the projection of B onto the plane. Now how it will behave? Because last time our column space was a straight line, but now our column space is a plane. And now we are trying to see how we can do this. So now in this situation, we have this particular column space defined by two columns, A2 and A1. These two columns represent two vectors, and a linear combination of these two vectors, A1 and A2, will make the whole column space. And in this situation, the column space is a plane. It is not just one dimensional line. For one dimensional line, we just need one vector or one column, but here we have two columns. So it means our matrix A consists of two columns. And these two columns, if you take a linear combination of these two columns, it will make a plane. So now we are dropping the B onto the plane. Okay, now if we drop the B onto this plane to find the projection P, how we proceed? The procedure is exactly the same. we will find an E vector between this P vector and B vector, which is B minus P, and we will assume that E is perpendicular to the column space of A. Now, the column space of A is a linear combination of two columns, A1 and A2. So again, we will start with the same basic assumption that our E, which is an error vector, is perpendicular, is at 90-degree drop onto this column space, which is a plane. Okay, and now we drop it and we'll find out that P is a vector which lies along the column space of A. And now, since the column space of A is made from A1, A2, so P is definitely x1 times A1 plus x2 times A2. Last time it was not x1, x2, it was just x. So if you keep comparing with the one-dimensional case that we solved, you can see very clear resemblance, and you can see how the generalization is happening. Now we have x1 and x2, whereas in that case we have just the x. Now our P consists of linear combination, and how to find the P? So we will just go with our equation, and our equation is that we wanted to find, okay, and we wanted to find this particular vector. And the equation is very clear now. The equation is that this particular matrix that we have, so our matrix, which is A, okay, this capital matrix A is perpendicular to E. Now, what is E in this case? B minus A x hat equal to 0. So this is the equation we have. So let me show you that equation a little bit in more detail. So in this case, what we are trying to say is that now you your matrix, which is A, has to be perpendicular to E. But in this case, since your column space is made from A1, A2, so both these vectors, A1 should be perpendicular to E and A2 should be perpendicular to E. So both of them should be 0. So A1 transpose B minus AX is 0. A2 transpose B minus AX. So this transpose basically tells these both equation tells you that your E vector is perpendicular to the whole column space. So this E vector is perpendicular to whole column space. So, and who is making that column space? A1 and A2. These are the bases. So we took the bases and we assumed it. So now if you look into the equations a little bit more carefully, what we find out is that the equation that we end up is this matrix A transpose times B minus AX is 0. So this is the main equation. This is the equation that will give us this x hat. So let's try to find the x hat. So if you open this equation, we will see that a new fact, which is what about, so if P, the projection is along the column space where the E lies. Now, if you think about E is perpendicular to the column space. So this E actually belongs to the left null space, and the left null space is N and with parentheses A transpose. So E belongs to the left null space, the null space of A transpose, whereas the projection belongs to the column space. Because column space and left null space are orthogonally complement to each other. So if something is not in column space, definitely it should be in the left null space. Since E is not in column space, then where is E? E is in the complement, orthogonal complement of the column space, which is actually the null space of A transpose. Okay, so now E is in the null space of A transpose, and we are going to find, and E is perpendicular to column space of A. Now, if you keep all those in mind, what we will find out is that now x hat is, you basically take this A transpose A whole inverse and you multiply it with the A transpose B. Now this x hat that you find now, because you bring everybody from the left hand side to the right hand side, and this becomes A transpose A whole inverse. Keep in mind that in one dimensional case we have A transpose over A transpose. This was our projection matrix. And now let's try to find the P. So P is A x hat So now if you put a x hat and you replace the x hat with this equation, because this equation gives you the x hat, the best possible solution. Okay, but keep in mind where this best possible solution came from. Okay, so if you go back a little bit, we will find out that once you open this equation, A transpose times B minus AX equal to 0, because A transpose is matrix A is perpendicular to E. Okay, so now if you look into this one, A transpose B minus A transpose AX. So now you take this A transpose AX, which is with the X hat, and you take it to the other side of the equal sign. So in order to do so, you have to take the inverse. So that's what you see right here. Okay, and you see here A transpose A whole inverse came on this side, and now X hat is alone, and you get this particular equation. Now the P is, your projection vector is now equal to AX hat, now A times this whole thing. And now let's look into the projection matrix. Now projection matrix is capital P. Now capital P is basically you, what is your projection matrix? Now your projection matrix is this thing which is under the line. So A, then it is A transpose A whole inverse A transpose. Keep in mind the order is very important. You cannot move this A to this side, or you cannot move this whole inverse to the front. No, you cannot change the order. Order is very important. Now you compare this one with the one-dimensional case. In the one-dimensional case, you have A transpose over A transpose A, which was in the denominator. Here your A transpose A is inverse. Now because you cannot put it in the denominator because it's not a number right now, it is a matrix. So you have to take the inverse, whereas there is a close resemblance. So A transpose A just jump up and come right between A and A transpose. So look at this equation. This equation and the one-dimensional case become closely resembled to each other if you assume that A transpose A has just P and come up in between A and A transpose. So now your matrix P is A into A transpose A, and this is your projection matrix for a situation where you have a column space that has more than one vector. So if your column space basis is more than one, then this equation will help you. Okay, so it's a more generalized equation. So let's assume for a time being a very special case, and a very special case is if your B belongs to the column space. Let's assume for a while that B is not something which is outside the column space. Let's say if it is in the column space, then what will happen? Then in this case, your projection matrix will become identity matrix, because in this case, your A, if you open this A transpose, so it means your A matrix will open up and it will become A inverse A transpose inverse. So this particular situation can only happen if A is a square matrix. So in this case, when A is a square matrix, A has A inverse. So if A is A inverse, then A into A inverse, this will become identity matrix. And this A transpose inverse and A transpose, this will also become an identity matrix. So the whole projection matrix become identity. You don't need to take projection if B is already in the column space of A. You don't need to take it. So this is where the projection basically doesn't make any sense. It becomes a trivial problem. But apart from it, you will find out that you basically need a projection matrix in a situation where B does not belong to column space of A. Now, if you have this situation, there are other two properties that we should keep in mind, that the projection matrix is a symmetric matrix. So it means P transpose is equal to P. Also, you should keep in mind that the second power of the projection matrix will bring you back to the projection matrix. So it's just like same as transpose. A transpose, you take another transpose and you get back to the original A. Similarly, if you have P and you multiply it with another projection matrix, you will end up with the one projection matrix. So you end up where you started from. So this is a situation you should keep in mind. Now, let's go into a very practical example, which is a least square fitting by a line. So if you have many points on a graph, In this situation, let's say we have only 3 points and we want to fit a line crossing these 3 points. So if you want to fit a line, so line has only two parameters, slope and y-intercept. So let's write down the equation c plus dt. So this is our equation. This is the straight line that we wanted to best fit, that represent these 3 points. These stars are the 3 points. So what we will do, we will find out the equations, okay, and we try to fit them. So let us say our equations are c plus dt equal to 1. First equation, c plus 2 times d equal to 2 is the third, and c plus 3 times d equal to 2 is the third equation. So you have these 3 points. Let me show you those 3 points, their coordinates. If I just go back and give, so the coordinates are 1, 1. This is the first point. The second is 2, 2. And the third is 3, 2. So these are the three coordinates, and we want to fit a line through these 3 points. So our equations will become um, c plus d equal to 1. This is for the first star. And for the second star, c plus 2d equal to 2. And for the third one, c plus 3d equal to 2. So that is how the equations will become. So these are the three equations that represents the 3 points, and we wanted to find a best fit line that goes through those points. So here you can see very clearly you have three equations and you have two unknowns. So it's clearly a case of tall matrix. So ax equal to b. And now if you look into very carefully, 1, 2, 2 is your b side, and 1, 2, 2 is not in the column space of this matrix. So if it is not, then the best we can do is find the projection of this 1, 2, 2 onto the column space of this matrix A. And that projection will be small p, which will be equal to capital P times B. So we need to find capital P. Now capital P is a projection matrix. So we have to find a projection matrix for this matrix A, because every time we change the A, the projection matrix will change. So the projection matrix will be defined in terms of this A, and then we will take the B and project it using that projection matrix onto the column space of A. If we do that, we will end up in this situation. So we have the matrix ax equal to b, which is 1, 1, 1, 1, 2, 3, c, d, and then on this side we have b, 1, 2, 2. Now we'll take the projection and we will find. So using the projection matrix, we will find x hat. So instead of x, because we cannot find x now, but we can find x hat. Yes, we can find x hat. So we'll find x hat, which will be using a projection matrix. We'll find the best fit line here. So I will just end my lecture 15 here, and we'll look forward to see other things which are eigenvector and eigenvalues next time. So this is a one useful way of using orthogonality, uh, to use projection to find solution for those systems of ax equal to b where b does not belong to the column space of A, so there is no chance of solution. So for that particular case, we have to use the projected solution, which is x hat. And in order to do this, we have to use the famous equation, which is A transpose A, and we use it to take it to the other side, and we find the x hat. So thank you very much. And if you have any questions, please, you can send me the comments on the YouTube or in the Google class. And with that, we came to the end of the lecture, and I will just finish off uh, my lecture now. Okay, thank you very much, and see you next time.